We're going to start now. So today we welcome Louis-Phillipe Nadeau. He comes to us mainly from Quebec. He got both his Bachelor of Science and his Master of Science at the Université Laval in '99 and '03 respectively, and then went to McGill University, which has a name that I can pronounce even though it's still in Quebec, and worked with David Straub, who got his PhD there in 2010. And since then, he has been a postdoc. He spent 2 years at Courant, where we have a preview visitor from Courant, New York University, with Dave Holland. And he's currently a postdoc at MIT with Raphael Ferrari. And you are heading relatively soon, right, to a faculty position at an ocean institute in Quebec, whose name I cannot pronounce. And he's going to talk to us about sort of a long-standing debate in oceanography whether the Southern Ocean should be treated like a jet, like the atmosphere, or like a gyre, like the rest of the ocean. But before he starts speaking, I guess I should remind people this is a class, so if you're signed up for it, you should sign in at the back if you want to get counted. And any graduate students who want to talk to Louis-Philippe about his work or just about life as a postdoc in general, you can meet and talk with him at 3. And I think if it's open, we'll probably try to meet in the Okogu room. But let me know if you're going to come so I can make sure that he goes there. But without further ado, Louis-Philippe.
Okay, thanks a lot, Chris, and thanks a lot for inviting me. Today I will talk about this current here, which is the ACC, the Antarctic Circumpolar current, which we see here in the time mean barotropic stream function. So as Chris mentioned, usually people, the classic view of the ACC is a zonally average one, where you average from west to east this circulation, and usually we look at a slice of depth versus latitude, and people are interested in the meridional circulation across the ACC. But now today I'm going to be interested more in this pattern of time mean barotropic stream function, looking at the latitude, longitude kind of maps, and specifically trying to understand how many streamlines goes into the Drake passage. So that's the zonal transport across Drake passage here. Every line here is 10 Sverdrup, so there's approximately 140 Sverdrup going to Drake passage here, and we want to explain this basic pattern. So of course, in an instantaneous kind of way, the ACC is very complex. So this is a model at 1 degree resolution. You see very few variability, but if you go to 1/6 of a degree, there's a lot of activity, eddy activities, and those eddies will affect how this mean pattern is at the end. So today the tools that I will use to study this problem will be very simplified geometry. So when I refer to an ocean in a box, I refer to the kind of ocean that are in the northern hemisphere, the Atlantic and Pacific, where you have a double gyre, a jet in the atmosphere driving a double gyre. And for the southern hemisphere, I'll just do an opening to represent Drake passage. And what's left of the basin region here, well, what's left of the box geometry, I'll call it the basin region here. And in the Drake passage latitude, I'll call that the channel regions. But I just start with this very simple experiment done by Allison et al., where they just take a simple GCM using Janet McWilliams parameterization, and they, well, setting the parameterization correctly, which mimics the effect of eddies, you get a reasonable ACC of 122 Sverdrup. And then they fill all this with land, most of the Indian and Pacific, and they observe almost no change in the ACC. But then when they fill this extra little part here, which corresponds to our basin region, well, they observe a very dramatic change in the ACC. And they argue that one must use weighted average of the wind stress over the path of the circumpolar transport of the circumpolar current to get the transport right. But the problem with this kind of idea is that you need to know the path of the EACC to use this idea. So it's not very predictive because you don't know the path in advance. So one thing that seems appealing is just to, if you do an experiment where you open Drake Passage, you note that, so here it's just an ocean in a box, and here I just open Drake Passage. You see that the circulation north of Drake Passage here is very similar to what happened before in the box case. So that it seems appealing to consider the ACC as the total transport as a sum of a basin contribution here and a channel contribution. And that's an old idea that goes back to Gill. And so that we'll first take this hypothesis as our first hypothesis and first consider the role of the basin contribution. So this very old idea that there might be a basin contribution that dates to Stormall. Basically, when you open Drake Passage, all those streamlines here should unfold and participate in the ACC. That's the idea. And if you follow that idea, you expect that the transport should increase linearly with the wind stress curve. But the problem is that all the numerical models show that there's saturation of the transport. So this idea has been totally dismissed over time. We tried to revisit this idea, but in a baroclinic sense, so looking at the two-layer ocean, you see that in a box, as you increase the wind forcing, basically you expect to put more and more momentum in the bottom layer, so more and more circulation in the bottom layer. And if you open Drake Passage for the upper layer and assume that, let's say, Scotia Ridge or some other topography will block the circumpolar current in the bottom layer, well, then you cannot rule out the possibility that there's a recirculation in the bottom layer that could be seen throughout the water column, and this part of the Sverdrup flux should be removed from the ACC. So here, well, we can use Ranson-Young, which is basically a way to predict the size of this recirculation in a box context to predict which part of the Sverdrup flux to keep. So here we see characteristics. Basically, you get the characteristics from the lower PV equation, and you simply, like when the characteristics hits the eastern wall, you expect no flow in the bottom layer. But inside the separatrix here, flow can develop in the bottom layer. So if you superpose this separatrix on the Sverdrup circulation, you can see that at first you expect that everything is top drop and is free to go into Drake Passage, but after a certain threshold, you can develop this recirculation to the east of a point called X0. And so as you increase the wind forcing, you increase the number of those lines, but you move X0 to the east. So this recirculation here becomes bigger and bigger. And if you do the math, you get a total saturation of the transport. So you increase the transport to a certain threshold, and then you saturate at a point that depends on geometrical factors. Okay, all this is good, but you still need to do something with the channel. So you need to add something for the channel itself. And that's where we come to the more classic view of ECCD. Normally you expect the eddies to transfer vertically the zonal momentum downward. So here is just a simple baroclinic instability experiment where you impose a shear, that's the upper layer string function, lower layer string function. And you see that after instability, the transport in both layers decreases. So that can be seen as like available potential energy transferring to kinetic energy. And that's really like the more classic view of the ACC, that eddies transfer momentum to the bottom, where it can be dissipated by a bottom friction or by bottom topography. And so if you just consider a two-layer case, you put some wind at the surface and you increase the slope of the interface between the two layers until you reach the condition for baroclinic instability. And then you transfer, your eddies will transfer momentum to the bottom where it can be dissipated. So this condition of baroclinic instability, if you assume that there's no flow in the bottom, no transport in the bottom, leads to a transport prediction, which is simply given by beta times the Rossby radius squared times the height of the ocean and the width of the gap. And we'll take this as our channel contribution and say that after this instability, when you increase wind stress amplitude, the basin contribution will take over, which is an hypothesis that will come back later in this talk. We'll kind of revisit this idea later. But, sorry about that. Microsoft error. I'm sorry about that. Yes, so we have our analytic model, which is this, again, I just repeat because okay. So some of the channel plus basin contribution. You begin with the background channel contribution, and then some kind of standard regime when there's no recirculation. After a certain point, you develop a very strong recirculation, and you saturate your transport. So we want to test this with a numerical model. We take a very simple PV model, QG model, which is based on the PV equations. You need to add some kind of mass conservation to it and zonal momentum conservation to it. If you want, we can discuss the details later. But basically, you code this and you get something like that, which you see here: potential vorticity and velocity magnitude, very rich eddy field with a simple peninsula here and jets in the ACC, everything. And if you look at timing stream function, basically you see the pattern that we saw before, some kind of basin region here and a channel like region here. And for the prediction, well, it fits qualitatively, but there's some kind of offset between the saturation expected by the analytic model and the numerical model. And we explain this offset by the north-south asymmetry between the gyres. So, okay, if you take that's upper layer and lower layer stream function for a box without topography. You see that there's a clear symmetry between the north and south gyre here. If you add the topography to the east here, to the west, you see that you create this asymmetry between the upper gyre and lower gyre. This gyre here is much less intense than this one. And when you open Drake Passage, well, then you have less of these streamlines participate to the ACC. Well, that's just an hypothesis. But another interesting thing before I go to the real meat of the presentation is the idea that bound friction can increase the transport. So normally in a channel, you expect that bound friction is basically your brake for the transport. Like, if you increase bound friction, you reduce the transport because it's friction at the bottom. But here, as you increase bound friction, you increase the transport, which is kind of counterintuitive. But if you look back to the framework that we described earlier, the bound friction will modulate the strength of the bound layer recirculation. And if you modulate the strength of this recirculation, then you get more transport when this recirculation is small. So this kind of framework seem to have some kind of advantage to explain parts of the system. But there's still the, yes?
So what kind of pattern topography you have?
Oh, yes, it's true. I should have shown. We can show it to you here. Looks like, oops, this one. Well, where did I put it? Yes. Looks like this. That's the. So it's basically meant to represent Scotia Ridge. Here you can see this part here as a continental shelf, and then this is Scotia Arc. So that's how the topography looks like. Okay, so but the question remains, what happens? So all this is, I guess, interesting, but the question remains: what happened when there is no basin region? So all that I presented earlier depends on the fact that there's peninsulas here and a basin region influencing this channel region. But when there's no peninsula, what's left of these ideas? And now we will study this case here, a channel with a topography without the peninsulas. And here it's just a setup as a meridional ridge and in a channel with applied wind. And again, I play the same game as I did before. I compare my box with a Gaussian ridge here. The exact same experiment without the wall. So it's a channel with the same ridge and a flat bottom channel for weak wind and strong winds. So what you can see from this figure is that here at low wind, at weak wind forcing, this simulation, this kind of circulation in the channel plus ridge case looks like a flat bottom channel. But as you increase the wind forcing, you get a clear signature of a basin-like circulation, if you like. So we're now interested in the transition between this kind of circulation and this kind of circulation, and how it affects the transport. So those are transport results for the flat bottom and the Gaussian ridge at different stratifications. Here I show the baroclinic transport because for the flat bottom case, the barotropic transport doesn't really mean anything because there's a very strong bottom layer of velocity. And basically what you can see is that the flat bottom case, in the flat bottom case, the baroclinic transport increasing following some kind of power law, whereas in the Gaussian ridge case, you have a complete saturation of the transport. And if you look at the barotropic string function, you see again this Sverdrup or like basin-like kind of circulation developing as you increase the wind forcing. And if I remove from this panel the analytic Sverdrup string function that I can get just using simple Sverdrup theory, I get this panel that I call psi diff. Psi diff doesn't change as you increase the wind forcing. So what this suggests is that basically you could, well, and just to try to convince you a little bit more, is here is a primitive equation simulation with 25 vertical levels and a very high resolution, and you see again the same kind of patterns in this simulation. So what this suggests is that this kind of circulation can be considered as a sum of a basin mode. Now, like the basin mode is not a contribution because it has no transport, and a circumpolar mode. So it's a change in the initial kind of hypothesis where basically this basin mode here just affects the momentum transfer in the channel. So as you increase the wind forcing, you put all the momentum in those gyres, but you don't affect the circumpolar mode. So we'll try to see if this kind of revised hypothesis can hold in different robustness experiments now. So here I just show you the vertical structure of the flow. This is the upper layer and lower layer for a box and a channel plus ridge. And it's just to show you that normally, like people, when you talk about Sverdrup circulation, we think intuitively of a linear kind of thing, but here you see the clear asymmetry between the north and south gyre and this very strong bottom layer of circulation, which is driven by eddy stretching of vortex stretching of eddies. So it's not a linear thing here. And well, you see that there's a clear similarity between the lower layers of circulation. So the idea is just that this will affect the total circulation such that it creates a saturation of the yes.
When you calculate the psi diff,
yes.
is the basin transport there linear or not linear? The SV.
SV is like really, it's just the linear.
Okay, so that's got a north symmetry.
Yes.
But then when you go to the next panel.
So so that's my point. Like if you average this, in the vertical, you get psi diff is 0 everywhere, which means that it's in Sverdrup balance.
Okay.
But
right. So
it's not because it's in Sverdrup balance that you can see that it's a linear kind of circulation, like eddy vortex stretching of eddies is very important in this case. And there's a lot of other stuff happening, but if you average in the vertical, you get simple like linear theory. That's what you expect at large scale for a very long average. And so now I do 3 robustness tests to test this kind of very simple hypothesis. The first one is varying the channel length. So if you think about it, if you vary the channel length, you'll vary the amplitude of this basin mode because you expect the gyres to scale with the width, well, the length of the channel. But there's no reason a priori to expect any change in the circumpolar mode. And here you go, when you do the experiment for a 4 by 3 1,000 kilometer, 4 by 6, 4 by 10, and 4 by 20. You see basically that you increase the strength of the basin mode, but the transport doesn't change. So what it means is that it seems to suggest that the circumpolar mode is not affected, but you modulate the strength of the basin mode by doing something like that. Okay, another test that you can do is increasing the bottom friction again. So if you increase bottom friction, here, let's concentrate on this panel here, which is a barotropic string function, barotropic transport. You see that as you increase bottom friction for a flat bottom experiment, you decrease the barotropic transport because it's your break in the bottom. But again, for the ridge, when you increase bottom friction, you increase the transport, which is, again, kind of counterintuitive. But if you see it with our hypothesis, you can see that when you increase the bottom friction, you modulate the strength of the basin mode, and you get you completely the basin mode completely vanish at high friction. So it kind of makes sense to talk about this in terms of basin, the sum of a basin mode plus a circumpolar mode.
Can you quantify that friction? Is it way above what you'd expect? Or,
yes,
or,
absolutely.
Yeah.
But I guess what's interesting here is that, so like normal friction is around here. But it's interesting to see that there's a regime where the saturation occurs. So like all the points here, that's for different wind forcings, they all collapse to the same value for a pretty wide range. So it means that the saturation that we observe is not coincidental to the specific choice of friction. And the last test that I will consider is just playing with the strength of the wind stress curl. So wind stress curl is driving the gyre in a closed box ocean. So you expect that if you decrease the wind stress curl without changing the average wind stress in the channel, well, you should decrease the strength of the basin mode and increase the strength of the circumpolar mode. And that's exactly what we observed. That's the solution for a sinus square wind stress, and that's the solution for a constant wind stress. So note that in this experiment, you don't vary the average momentum input in the channel. And that's the result for a flat bottom channel. So you see that basically removing the wind stress curl kind of explains half of the difference between the flat bottom case and the reference case. And again, what happens is that when you decrease the wind stress curl, you completely remove your gyres, and you end up with this weird solution with strong jets at the boundaries. And that's, again, a solution for the GCM, which seems relatively similar to what we observed in QG. And lastly, for this section, just an analysis of the momentum balance. So I've been talking a lot about momentum transfer, but here we'll try to quantify this a little bit. So that's the basic momentum balance that you expect. You expect wind input at the surface, and those two terms are interfacial form stress, so the effect of stretching of eddies, and this is Reynolds stresses due to the relative vorticity. And in the bottom layer, you expect topographic form drag to be the main sink of momentum. So this term, the interfacial form stress, is in our simulation and in most simulation in the literature much bigger than the Reynolds stresses. So we'll consider this term as the main mean by which momentum is transferred from the upper layer to the lower layer. And now we just look at a decomposition in wave number of this term, the form stress. And basically, the only thing that I want to show you is, on average in the channel, you have this very strong peak at high wave number for the flat bottom case, and that's your eddies. That's your geostrophic eddies. The classic view of the ACC, when you have baroclinic instability, you transfer momentum downwards via your geostrophic eddies. But when you add the ridge with the wind stress curve, you have a switch from high wave numbers to lower wave numbers, which means that you transfer momentum at larger scale. And those larger scale are the time mean standing eddies, which is basically our
Excuse me, so what that 10 means in terms of real number?
what's that?
What that wave number 10 means in terms of kilometers? Roughly.
So wave number 1 would be the basin.
Okay.
So like 10 would be 1/10. So basically, this peak corresponds to the western boundary curve. So if you go back, it corresponds to this thing, that very big standing wave, and that's where you have your biggest meridional velocity. So it's not very surprising. It's where you have your highest momentum transfer. So just a summary of this part. Just at the beginning, I talked about this kind of circulation as a sum of a basin contribution plus a channel contribution in the storm regime. In the saturation regime, it wasn't very clear what was the channel contribution, because basically everything came from the basin region. But if you consider this kind of revised hypothesis, well, it doesn't really change the analytic model. It's just that you can see this kind of panel here as the sum of basin mode affecting the momentum transfer of the circumpolar. So it's just a kind of another way to see the same thing. But I think it's more meaningful physically to see this as affecting the momentum transfer in the channel, such that this mode doesn't change. And finally, I'll just finish quickly with a more realistic case with a realistic topography. So until now, I used this kind of Gaussian topography, but I'd like to understand if the things that I talked about in this case apply to the realistic topography case. So just movies of the circulation for the Gaussian case. You already see it, full of jets, very strong Rossby waves in the background here going westward. And then if you put the realistic topography, you have this very complicated pattern of jets, but that seems to be set by the topography.
When you say realistic topology, do you mean throughout the entire latitude range, or?
Yeah, so what I do here, like, it's really like I take data.
Yeah.
That's like Patagonia and Australia,
Yeah.
and I take the real data and I map it to
Right.
make it similar to what I get. And so it changed quite a lot of things. It changed the transport. And surprisingly, it changed the transport such that it fits much better our little analytic model. And the transition, so if you do a linear transition between this and this, you see that the transition between the two happens very, very, very rapidly. And essentially, we explain this fact by the, well, that's a little bit a parenthesis to the story, but when you have this kind of topography, you concentrate all the momentum transfer into one place, which is here, and you develop this very strong recirculation in the mouth of Drake Passage. And eventually, when you switch to realistic topography, you lose this recirculation between here and here, and that's where you observe the dramatic change in transport. So whether this kind of circulation still exists in this kind of geometry is debatable. I think this, my take on it is that the fact that there's a good agreement with the analytic model suggests that this kind of ideas seem to apply in this case. But yeah, to see if it applies in the real case is still another story. And I let you decide if I convince you or not. But I'll stop here. I think so.
Questioning.
Yes.
Could you go back to the previous slide where? No.
Which one? This one?
No. That one.
This one?
Yeah, it's the top panel. I wasn't quite clear.
Oh, I'm sorry. Yeah. So, let's say you call this. I don't know. Like you have an expression for this as A and this as B, and you do a continuous transition between A and B. So like here it's purely Gaussian, and this is purely realistic, and you can do a transition between the two just by addition, basically. Just linear superposition.
So you keep adding the.
Yeah. So like let's say here it's just like half and half, and this is purely realistic and or purely Gaussian, and this like you see the transition, how the flow gets deformed and the topography has changed from one to the other.
Just gradual go to topography or?
Well, no, it's just that, let's say this is A, like at first I take 1A plus 0B, and then like in the middle at 0.5 here is just 0.5 this times plus 0.5 that. It's just very simple linear transition.
Oh.
Yes?
In the realistic topography case, how realistic was your wind stress curve?
It's still the very same super simple, so but you get a lot of variability and complexity just with the rest of
I have one other quick question. In that two-layer momentum balance
Yes.
you showed, could you just remind us, what was that interfacial stress, that interfacial friction term? Could you just, what was the physics?
Okay, so
Not the Reynolds stress term, but the other one. Yeah, that one, interfacial.
the interfacial one.
Yeah.
So okay, so let's say you have a ridge at the bottom, and you just have one layer. You'll have a flow that goes over this ridge. You'll create a high pressure in the front and a low pressure in the back, and by gyostrophy, just deflects the current northward and southward, and that's a way to sink your momentum down. But like that process can happen between two layers of different density.
Okay.
And what happens is that it transfers, like the net effect is that it transfers momentum downward.
Okay.
Until you arrive to topography where solid Earth just deflects.
Thank you.
So in this case, the bottom friction doesn't appear in this momentum balance.
Yeah,
just
because
it's very small. Or
yeah, it's neglectable when there's bottom topography. Well, ideally that's what you want. But yes, and we did the experiment.
So how will you tie this to the MOC?
Oh, that's a very good question. So like I began the discussion by saying that most of people are interested in the MOC. I'm like coming from a very different point of view, and my goal is eventually to try to link. I guess I'd like to link that kind of circulation with the MOC, but it's very.
But do you know what kind of circulation you actually get out of this kind of model?
Oh, but that's very simple. Like the residual circulation is zero in a QG model by definition. But if you go to a more realistic model, you'll get it will essentially depend on that's a whole different type of, but like it will depend on the surface heat flux that you impose at the surface and the way it's linked to the gyres of the north.
So it gets very complicated.
Yes, complicated, but you kind of see it here. Like of course, like I guess the divide between like the two, the MOC will be higher here, for example. I guess how it linked with this kind of recirculation, I don't know. That's an interesting question.
So one more question back to this instability part. So once you have this so-called realistic topography, so the whole argument for baroclinic instability is no longer works, right?
The
baroclinic instability, the one that you start with.
Why is it?
Because the topography can mess up the
No, I think it's
all your stability.
no, but because you still need eddies to transfer momentum downwards. Like it's the main mechanism.
But your beta effect.
Like let's
is
say you have
always
a
up.
lot of layers, you need to transfer from the upper layer to the lower layer when it can be dissipated by topography. So you still need this mechanism to transfer momentum down. So no, I think that the whole argument is still like it's just that in this case, like the argument that everybody does in a straight channel, you do it along the path of the street. So like if you average follow the path of the ACC, you get the same argument that A is transformed.
I had a question about jets that you see in the, I don't remember which simulations, but in a lot of them.
This one?
Well, the more regular ones. So
Yeah,
there's,
those ones.
did you do anything to look at what sense the spacing and number of the jets that you get?
Well, I've done it in much simpler context. Like I have a project we can talk about on this, but in this case, yeah, it's very complicated because I guess it's linked with the bottom layer circulation also. My guess is that this place would fit the separatories that we talked about earlier.
And is this in the bottom layer or the top layer that you're showing?
This
Or-
is the upper layer.
Okay.
Circulation.
Any more questions? Oh, let's thank our speaker.